Welcome to our presentation on making web-based accessible computer science applications for K-12 students with disabilities. We hope you will enjoy our presentation. We would like to briefly introduce ourselves. Dr. Daniela Marghitu received her BS in Automation and Computing from Polytechnic University of Bucharest, and her PhD degree in Automation and Computing from University of Craiova. She is a faculty member in the Computer Science and Software Engineering Department at Auburn University, where she has worked since 1996. She is the co-principal investigator of NSFCISE, EAGER, an accessible coding curriculum for engaging underserved students with special needs in after-school programs. For more info, see her official site http://www.eng.auburn.edu/Daniela. Meenakshi, Meena, Das is a master's student studying computer science at Auburn University, where she is a graduate research assistant working on accessible computing education under Dr. Daniela Marghitu. This work has resulted in 2 publications at the International Conference on Human-Computer Interaction, and she was also named an NCWIT Collegiate Award finalist. According to the U.S. Bureau of Labor Statistics, the employment of computer and information research scientists is projected to grow 15% from 2019 to 2029, much faster than the average for other occupations. However, individuals with disabilities are less likely to pursue science, technology, engineering, and mathematics degrees. Let us look at some of the reasons why this happens with a focus in computer science education. One of the important factors is lack of accessible interfaces and learning software for students with disabilities. Many of the IDEs, be it text programming or block-based programming, are not accessible to students with disabilities. Let us take the example of a blind user, who uses a screen reader as an assistive technology to navigate a computer. Screen readers such as JAWS, NVDA, and VoiceOver render text or image content on screen as speech or braille output. Many IDEs may be inaccessible or partially accessible to screen readers. By partially accessible, we mean some of the features such as, say, debugging, may not be accessible. Let us now take the example of users with motor disabilities. Individuals with motor disabilities cannot easily operate the keyboard. They may rely on input modalities such as speech, eye gaze, or switch control. Speech-to-text is a useful interface for individuals with motor disabilities to program and is gaining prominence in recent days. Dragon Naturally Speaking is a speech recognition software and is widely used for programming by voice. There are also applications such as VoiceCode, Serenade and Talon Voice which provide capabilities to write code using natural speech. Talon also provides ability for eye tracking. There are certain motor disabilities which affect speech as well. For example, many users with cerebral palsy or closed head injury are unable to use speech recognition programs because they may also have dysarthria, which is reduced speech intelligibility caused by neuromotor impairment. In such cases, augmentative and alternative communication methods can be used, or speech recognition systems can be trained on different speech disabilities using AI to recognize variety of speeches. AAC devices can also be used by students with certain cognitive disabilities. American Sign Language, ASL, is the first language of estimated 500,000 people in United States. Still, there is a dearth of ASL instruction in computer science. Sign language instruction can be very useful for prelingual deaf population who learn signing as their RST language. There have been many efforts to make computer science education accessible using ASL instruction. The University of Washington created an online ASL STEM forum to develop standardized ASL vocabulary for many technical concepts and terms. Since ASL has a widely dispersed user base, these standardized vocabulary are needed for deaf individuals to learn technical concepts effectively. However, there is still a lack of ASL computer science education resources, and ASL interpreting is not always available. This shows us that there is a need for multimodal accessible interfaces, which work for a variety of different individuals. Programming has largely been a visual activity. This is changing with the evolution of accessible multimodal interfaces. Different people learn in diverse ways, hence utilizing multimodal learning strategies is immensely important. Using images, graphics, and other media content can be very useful for students with disabilities to learn, rather than providing just textbook content. CS Unplugged activities are becoming very popular to teaching computer science fundamentals to K-12 students. These involve using paper, pencil, or physical manipulatives to teach basic computer science concepts to students and have proven to be quite effective. Tactile materials for blind students can be effective in learning computer science. For example, a puzzle or a robot navigation map can be printed with a braille embosser so blind users can successfully access them. The Universal Design for Learning framework is becoming immensely popular for education these days. According to the Disabilities, Opportunities, Internetworking, and Technology Center at the University of Washington, a universally designed for learning (UDL) curriculum in formal and informal settings reflects an awareness of the unique nature of each learner and the need to address differences by offering multiple means of representation, multiple means of action and expression, and multiple means of action and engagement. Hence, multimodal learning strategies should be increased. By using existing tools such as Microsoft's Accessibility Checker, many common accessibility issues such as missing alternate text, insufficient contrast, and structural headings can be remediated. One of the most important characteristics of an accessible PDF is that it should be tagged. PDF tags provide a hidden, structured representation of the PDF content that is presented to screen readers. Adobe Acrobat's accessibility feature provides auto tag amongst several other accessibility features. Due to COVID-19 pandemic, much instruction has shifted to recorded lectures. In this case, captions are crucial for the deaf or hard of hearing audience. If these documents are made accessible and videos are captioned from the start, many classroom accommodation requests for document accessibility can be prevented. This goes back to concept of universal design of learning, which aims to make products or services accessible from the outset, and has emerged as a popular framework for creating accessible instruction methods. Moreover, teachers should not let their implicit biases and stereotypes towards people with disabilities set low bars for them. Now that we have talked about some of the issues, let us talk about how we can use the web to remediate some of the issues and make computer science K-12 education accessible to students with disabilities. We choose the web for the following reasons. Most popular platforms to teach coding to kids, such as block-based programming, are web-based. By using web, no time spent on installation, and students can jump right onto learning. They can also access it via multiple devices such as mobile, tab, or laptop and save progress on the cloud. The web content accessibility guidelines are also well established, but not all web apps to teach programming to K-12 students with disabilities are fully accessible. Next, we will discuss this in the context of block-based programming, which are popular web learning apps used to teach coding to K-12 students. The rest of the presentation will focus on techniques to make block-based programming accessible. Applications such as App Inventor and MIT Scratch are commonly used to teach computer programming to K-12 students. They depend heavily on visual cues and mouse input for drag and drop, which make them inaccessible. In order to make them accessible, we asked the following research questions. What interaction techniques can blind individuals use to understand the structure of a block-based program? What interaction techniques can blind individuals use to receive non-visual feedback from a block-based program? What interaction techniques can blind individuals use to debug a block-based program? What are the uses of a screen reader versus a non-screen reader approach? There has been substantial effort in making block-based programming accessible to individuals with vision needs. Google released their accessible version of Blockly, which replaced the drag-and-drop layout with a text layout for screen reader compatibility. Researcher Stephanie Ludy's work mainly focused on adding screen reader capability to Blockly, along with keyboard navigation, while maintaining its original block-based interface. Google later re-released their own version of Blockly with keyboard navigation for its blocks. Although the blocks in this current version are navigable by keyboard, they neither produce audio output nor are accessible via screen readers. With regards to non-Blockly projects, the following has been done. Researchers Milne and Ladner created Blocks for All, an iOS touch-based tablet application which is accessible via VoiceOver. Researchers Kaushik and Lewis have proposed a non-visual blocks language called pseudo-spatial blocks, which distorts spatial layout, and is based on T. V. Raman's idea that instead of making spatial visual data accessible to screen readers, the focus should be on making better non-visual representations of information. Their application uses synthetic speech instead of a screen reader for providing output, although they state it will be possible to add screen reader support to it as well. Now let's talk about why we used Blockly for our accessibility efforts. The most common reason is that most popular block-based coding applications such as Scratch, Code.org, App Inventor use the Blockly library as their base, which means they built their applications on top of Blockly. Hence, adding accessibility to Blockly is an appropriate choice. Blockly is also web-based, so users don't have to do any heavy installations. It is also a client-side library with no server-side dependencies, which is another plus point. When Google conducted user studies with their initial accessible Blockly approach, they found that many students were not comfortable using a screen reader. One of the most popular screen readers, Job Access with Speech, JAWS, is also quite expensive. Some of the students come from low socioeconomic backgrounds and hence may not have had the financial means to purchase such screen readers. Mac computers come with a free screen reader called VoiceOver, but a Mac itself is quite expensive. Moreover, learning to use a screen reader requires considerable practice and immersion, making it challenging for users with recent vision loss to become adept at. Therefore, we initially developed a non-screen reader, self-voicing solution using synthetic speech and interactive text-to-speech approaches. The ability to use a screen reader adeptly should not be a prerequisite or a barrier to learning to code, and hence we took this approach. The Individuals with Disabilities Education Act requires that students with disabilities receive education in the least restrictive environment, that is, alongside their non-disabled peers. We make this possible by using a spatial approach to convey information, instead of non-visual approaches which distort spatiality. Although non-visual approaches have been shown to have immense learning uses for blind users, they are not very useful if blind and non-blind individuals want to collaborate and work together. Peer programming is commonly used in professional settings and also utilized by teachers in classrooms. Our approach maintains a spatial yet accessible organization of the block-based coding platform, making it easier for sighted and non-sighted peers to collaborate and learn programming together. Auditory cues such as earcons are distinctive sounds that convey certain information. In studies examining teaching robotics to blind K-12 students, earcons were shown to improve learning of coding concepts. In addition, using non-speech audio cues such as earcons can greatly reduce the cognitive burden that comes with sole speech output. Research has shown that sounds produced from different spatial locations are easier to distinguish. For example, when you play video games, you can hear certain audio sounds from only the left or right ear of the headphones, or certain sounds can feel nearer than others. Audio software enables this process by specifying audio coordinates in a 3D space. This is called binaural spatialization, and we use this technique to assist students to understand the opening and closing of nested code blocks. For example, a click sound is heard through the left and right side of the earphones respectively to denote the opening and closing of nested blocks. Let us quickly talk about binaural spatialization. For example, at the beginning of a nested block denoted by red line, a click is heard through the left side of earphones to signify the opening of the nested block. Now, at the end of a nested block denoted by the yellow line, a click is heard through the right side of earphones to signify the closing of the nested block. Web libraries such as Web Speech API and Web Audio API make it very convenient to implement these features and work on all major browsers. Now, let's look at a demo of the text-to-speech feature.
Logic. If-else block. Logic compare block. Logic operation block. Logic negate block. Logic Boolean block. Loops. Repeat block. Repeat while or until block. Repeat while or until block. Block connection. Repeat. While. Input connection. Connection marked. Logic. If-else block. Logic compare block. Logic compare block. Block connection. Logic compare block connected. Repeat while or until block. Left operand. connection marked, logic, loops, math, number block block connection, number block connected to logic compare block. 123 equals, right operand, connection marked, logic, loops, math, number block block connection, number block connected to logic compare block. 123 do, connection marked, logic, loops, math, text, print block block connection, print, input connection, quote, ABC, hello.
We evaluated our solution with 4 participants with varying vision need ranging from low vision to total blindness. 2 of these were experienced programmers, while the other 2 were low or inexperienced in programming. This was done to examine a variety of feedback. The participants were given some simple warm-up exercises such as entering the toolbox and navigating its categories and blocks, followed by a combination of tasks such as writing code that prints Hello World using the repeat block, and some debugging exercises. Major feedback revolved around improving audio, personalization, and improving cursor. One strong feedback from experienced programmers was adding screen reader functionality instead of text-to-speech since they were already proficient with screen reader and didn't want to turn it off. We modified our solution to send audio through screen reader, and tested it on Mac's VoiceOver and Google Chrome. Now let's look at a demo of that.
Chrome, 127, Blockly Workspace, Group, with 6 items. You are currently on a tab, inside of a group. To select this option, press Ctrl, Option, Space. To exit this group, press Ctrl, Option, Shift, up arrow. Logic. If-else block. Logic compare block. Logic operation block. Logic negate block. Logic boolean block. Loops. Repeat block. Repeat while or until block. Repeat while or until block block connection. Repeat, while, input connection. Connection mark. Logic. Loops. Math. Loops, logic, if-else, logic compare block connected to repeat while or until block. Left operand. Connection mark, logic. Loop, math, number block connected to logic compare. 123, 123, contents select 3, 12, 3 equals. You are currently on a tab, inside of a group. To select this option, press Ctrl, Option, Space. To exit this group, press Ctrl, Option, Shift, up arrow, right operand, connection mark. Logic. Loops, math. Number block connected to logic compare block. 123, 123, 3, 3. You are currently on a tab, inside of a group. To select this option, press Ctrl, Option, Space. To exit this group, press Ctrl, Option, Shift, up arrow, do, connection mark. Logic, loops, math. Text. Print block connection, print block connected to repeat while or until print. Input connection, left double, ABC, hello. You are currently on a tab.
You can see from the demo that a screen reader will speak a few things which are irrelevant to the user. A high school low vision student with low screen reader proficiency said that screen readers repeat words and read out unnecessary information, so she preferred the text-to-speech. This could also be due to the fact that she was not totally blind and mostly relied on magnification software to navigate computer. However, she enjoyed the text-to-speech feature and said it made her experience more accessible. On the other hand, as we mentioned before, the experienced screen reader users preferred the use of screen readers. Screen reader skills are important for a blind user, so in no way we say they should not build screen reader skills. However, we believe screen reader proficiency should not be prerequisite to learning to code. Hence we developed both text-to-speech and screen reader approaches, that is, providing multimodal interfaces. We briefly touched upon earlier how programming using voice is becoming popular for users with motor disabilities. Individuals with motor disabilities, that is hand, shoulder, cannot easily operate the keyboard. They may rely on input modalities such as speech, eye gaze, or switch control. However, most of these technologies work for text-based environments, and not block-based programming environments. We will now discuss how to make block-based programming apps accessible using speech-to-text web libraries. Let's talk about some related work to make block-based programming accessible to those with motor disabilities. Voice programming for Scratch, a popular block-based programming app for K-12 students, has been researched before. Mina, a tool developed in Java, runs parallel to Scratch as a voice recognition system. When Mina is started and Scratch is opened, users can create programs within Scratch solely through voice. However, this is a desktop-based solution. This speech-to-text approach utilizes Google's keyboard navigation feature to control blocks. A JavaScript library called Anyang is utilized, which allows for users to add voice functionality to their applications. Anyang receives the voice commands from the user, and dispatches a Google Keyboard navigation event mapped to that command. In the later design, we also make use of natural language processing lightweight library compromise to increase the accessibility of the speech-to-text workflow. Let us talk about the initial design. In the table, you can see the list of supported voice commands. Every voice command was mapped to a single keyboard event. For example, when a user says toolbox, the toolbox of blocks will be shown. When a user says, next, the cursor will proceed to the next block of code. Saying these individual commands is quite time-consuming and adds cognitive load on the user. Let us look at a demo to understand this better.
Toolbox, toolbox, next, 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 previous, previous, in, next, next, select, next, next, mark, toolbox, next, 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 in, select.
In the demo, it took around 20 voice commands to finish the task. In an improved system using natural language processing, voice commands are mapped to multiple keyboard events so that users can have a better experience. Let us look at another demo which uses natural language processing to understand this better. We will demo the same task of adding a count block with a nested print block on the workspace.
Go to Math, go to Text, Loops, go to the Count with block, select, go down 2 times, mark the connection, go to Text, go to the Print block, select, go up. What does this block do?
Have the variable I take on the values from the start number to the end number, counting by the specified interval, and do the specified blocks.
In this demo, as you saw, it was a much natural way of communicating with the interface. It also only took about 10 voice commands as compared to 20 in the initial demo, thus saving time and reducing the cognitive load for the user. Let's finally talk about some uses of natural language processing. Fitts' law states that the amount of time required for a person to move a pointer, for example mouse cursor, to a target area is a function of the distance to the target divided by the size of the target. Thus, the longer the distance and the smaller the target's size, the longer it takes. Our aim is to reduce this required time by using natural language processing. Natural language processing model can also be trained on variety of voices and accents to improve recognition, thus enhancing accessibility. Web libraries such as Anyang for speech recognition and Compromise for natural language processing make it very convenient to implement these features and work on all major browsers. We briefly touched upon earlier how to make computer science more accessible to deaf or hard of hearing individuals. Let us now talk about some statistics. Deaf individuals often acquire sign language as their first language, and they are most fluent and comfortable in it. Half of deaf students pass from secondary school with a 4th grade reading level or less. The frequently reported low literacy levels among students with severe hearing disability were partly due to the discrepancy between their incomplete spoken language system and the demands of reading a speech-based system. This shows the need to produce computer science content in ASL. Work has been done to produce American Sign Language content for computer science videos. Apple recently released 8 computer science concept videos in ASL. ASL has produced signs and denitions for vocabulary and concepts such as recursion, debugger, linked list, and variable. In this way, computer science jargon is being made accessible to older students who are deaf, who have to otherwise rely on spelling while communicating with this vocabulary. Prelingual individuals who were born with deafness, became deaf very young and learned American Sign Language since childhood will more likely be interested to learn coding through American Sign Language. We now discuss how a block-based environment may be made accessible for those who are deaf or hard of hearing. This is based on the heuristic evaluation for deaf web user experience. This heuristic evaluation is based on the well-known usability heuristics developed by Jakob Nielsen. It consists of similar heuristics as Nielsen's and provides additional context with regards to accessibility for the deaf or hard of hearing. As described before, sign language content is crucial for prelingually deaf audience. In collaboration with the organization Deaf Kids Code, we developed computer science concept videos in ASL. Let us look at a short demo of one where a native ASL signer explains if-else computer science concept.
If one thing is true, do a specific action. If not true, do another action.
Good visual feedback is very important to ensure web accessibility for the deaf. For example, when a user clicks on the Run button to execute their code, it is necessary to provide clear visual cues such as text or graphics on screen, which can convey that the program has been run, as opposed to just audio cues. There should also be match between website and the world of the deaf. The website should be aligned with language and concepts from deaf culture. Thus, only ASL experts participated in the making of our videos to ensure authenticity and correctness. Evaluation was also done with 4 ASL signers and their feedback is being evaluated to improve our videos. ASL signs for every drag and droppable block, like, if else, or, while, are displayed as tooltips for a block. Tooltip is a common graphical user interface element. It is used jointly with a cursor, commonly a pointer. A research study conducted with 15 deaf users found that sign language and picture tooltips were very positively rated as opposed to only text-based tooltips or a human-speaking-based tooltip. In our web application, once a user hovers their cursor over a block, it will play the sign for the block in ASL. However, if the user would prefer only text as tooltips instead of ASL, they have the option to change to only text view as well. This ensures users have control on the features of the web application. Here is a demo of the tooltip functionality in action. You can see as a user hovers over the repeat times block, it provides information in ASL as to what that block does. As you saw, every ASL video includes captions to account for postlingual deaf who became deaf later in life and prefer captions. Our application aims for web content accessibility conformance, that is using adequate color contrast, allowing zooming, minimizing distracting and cluttering content, and using proper headings. Hence, visual noise is eliminated to reduce memory overload. This will also be useful to individuals with cognitive disabilities. Graphics, pictures, videos, and the different forms of multimedia can facilitate learning of complex computer science material, which can be challenging for deaf students that do not know how to use sign language. Hence, we incorporate multimodal learning which is useful to deaf and hard of hearing individuals. Multimodal approaches as we discussed involve the use of multimedia along with the text and encourage the use of interactive literacy practices between teachers and the students. To conclude, let's talk about some key points of this presentation. First, we saw that providing accessible multimodal interfaces to learn computer programming is essential for K-12 students with disabilities. The accessible interfaces may range from providing text-to-speech or screen reader support, speech-to-text, and providing sign language interfaces to name a few. Next, we saw why accessible curriculum ranging from accessible PDF or Word files, captioned videos, and following principles of universal design is important. We also discussed why web is a powerful medium for K-12 students with disabilities to learn computer programming and the different ways we can make them accessible. Last, we educators, researchers and developers need to remember that accessibility is a right for every K-12 student with disability to learn computer science. Computer programming is a growing and important field of the present and future. When the tools to learn programming from an early age are inaccessible to people with disabilities, we are denying them the opportunity to succeed. Though there has been an increasing push to educate and retain students with disabilities in computer science, encouraging these students is practically meaningless if the technology and instruction are themselves inaccessible. We should aim to bridge this gap between inclusive intentions and inclusive practice. We should strive to break this barrier and make computer science literacy, education, and, ultimately, careers accessible to all. This work has been made possible due to NSF grant, EAGER, an accessible coding curriculum for engaging underserved students with special needs in after-school programs and a special interest group on computer science education special projects grant. Here is a list of references used in the presentation. We hope you enjoyed our presentation.